Okay, so you got a bubble. The bubble can be up here at the surface. The bubble can be down here at the bottom of the lake. Okay. Now you want to know the density of the water. So you want to know the pressure of the water, right? So the pressure is given by the density of the water times the gravitational acceleration of the Earth, g, times the height, right? dgh. So they give you the density, you know that one. This is a constant, 9.81 meters per second squared, so you know that one. The key here is that since you want to find the height of the water, which is really the depth of the water, right? There's your h. The height is going to be pressure over dg. Right? Just make sure you have the correct units in there. MKS. So try to get the pressure in newtons per meter squared. Okay, that should give you the correct height in meters anyways. So how do you find this pressure? So what they do is you say, look, we're talking now about this bubble. The bubble is a gas. It's air, and it should obey the ideal gas law. So that means PV equals nRT is true up here, but it should also be true down there, okay? So if that's true, then you can use the combined gas law. P1 V1 over T1 equals P2 V2 over T2, okay? Now remember, when you're dealing with gas laws, temperatures have to be in Kelvin, so whatever temperatures they give you in Celsius, you got to convert that to Kelvin. They give you the volume. The volume can be in milliliters for both of them, or liters. It doesn't matter what the units of the volume are, as long as they're the same, because the volume units are going to cancel out anyways. And it's arbitrary which one you call 1 and 2. So you could call this up here P1, V1, and T1, those three up there, and P2, V2, and T2 down there. Or you could do it reverse. You could have 2 up at the top and 1 at the bottom. It doesn't really matter because it's arbitrary which one you pick anyways. But you're looking for one of the pressures. So let's say it's the pressure down here, right? And because you need this pressure, and that's P2, based on what I'm saying. So you're just going to solve for P2, right? So what you do, you cross multiply. Multiply both sides by T2. Divide both sides by V2. Again, they give you the volumes. You know this is 1 atmosphere up here. But 1 atmosphere is, I think, it's 100... It's 1.01325 times 10 to the 5th newtons per meter squared, which is the same as 101.325 kilopascals. Kilopascals is really MKS system. It just has a prefix in it. But if you want to have it in the pure MKS units without prefixes, it's right there. Okay? So that's going to, when you solve for your P2, that's going to give you MKS, right? So make sure this is in Kelvin. Again, doesn't matter what that unit is or that unit is, just as long as they're the same, the units will cancel. This has to be in Kelvin. And then your P1, well, you know, P1 is up here, right? 1 atmosphere, so that's 1.01325 times 10 to the 5th newtons per meter squared. Now that might give you an answer, it's going to give you an answer down here that's in newtons per meter squared. So what do? If they wanted in atmospheres, you just say, look, 1 ATM is 1.01325 times 10 to the 5th newtons per meter squared. Right? That's the conversion of pascals to atmospheres. So you just do a conversion factor. So if you end up with a pressure that's like, 5 times 10 to the 6th newtons per meter squared, you're just going to multiply that by 1 ATM per 1.01325 times 10 to the 5th newtons per meter squared. And that'll give it to you. You should get it. I'm trying to think. I forget what the volumes were. I don't remember any of the numbers you gave me. But remember, it's going to end up being more than 1 atmosphere down there. It's probably 5 atmospheres or 10 atmospheres or something like that. It's not going to be 1 million atmospheres, and it's not going to be 1.5 atmospheres. Okay?